Welcome back to episode 2. In this episode, we will explore CESS's technical architecture and discuss each industrial challenge and the key technologies that enable CESS to solve these challenges in detail. Once we understand the technologies that solve these industry challenges, we will go through the client interaction model to understand the process of uploading and downloading files on the CESS network. So without further ado, let's start with the platform architecture of the CESS network, and we'll start from the bottom up.
At the foundation of the CESS network, we have the blockchain layer, which consists of consensus nodes. These nodes maintain the blockchain, serving as the distributed ledger for the entire CESS network. They're responsible for validating transactions, producing blocks, and participating in network governance. In addition to that, consensus nodes verify storage and distribution incentives to nodes contributing to the network. The CESS blockchain supports both EVM and WASM smart contracts, enabling developers to build versatile and scalable applications. It operates using the random rotational selection R²S consensus mechanism. This ensures efficient and decentralized consensus across the network. Above the blockchain layer is the distributed storage research layer, which includes storage nodes and trusted execution environment nodes. Storage nodes provide storage space and securely store user data in exchange for incentives. Trusted Execution Environment Nodes, or TEE nodes, play a crucial role in ensuring data integrity by computing and validating storage-related proofs, or PODR and POIS algorithms. This process guarantees that the storage nodes are genuinely providing the storage space and storing user data, maintaining the security and reliability of the network in a verifiable way. Next, we have the CDN layer, which consists of CDN cacher nodes and CDN retriever nodes. CDN cacher nodes optimize content delivery by caching frequently accessed data, reducing latency, and improving network efficiency. CDN retriever nodes are responsible for retrieving file segments from storage nodes, assembling them, and delivering the completed file back to the user. In addition, CDN nodes also provide location-based storage services, or LBSS, and load balancing, ensuring fast and efficient content distribution. Above the CDN layer, we have the services layer, which provides various access points for developers and users to interact with the CESS network. DEOSS, or DOS, and other light gateways in this layer expose CLI, RPC, SDKs, and APIs, making it easier to integrate CESS services into many applications. These services act as a gateway to the CESS network, abstracting complex operations and streamlining user interaction with decentralized storage, retrieval, and computation. At the top of the architecture, we have the application layer, where the application interacts with the CESS network via the services. Some key applications include dshare, which is a decentralized data sharing solution, dcloud, which is a decentralized cloud storage service, CESScan, which is a blockchain explorer for monitoring network activity, and a third-party application, such as Telewelly, a decentralized TikTok, AnonID, a decentralized biometric authentication application, and many more that leverage CESS for secure, decentralized data infrastructure. On the right side of the architecture, we have the CESS AI Agent Hub, which interacts with the XS AI protocol suite. The core component of this suite is CESS AI Link, which integrates federated learning mechanisms. This allows participants to train shared AI models without compromising or exposing their original data. CESS AI Link utilizes smart contracts to delegate computational tasks to various nodes, ensuring optimal resource utilization while preserving data sovereignty. This suite enhances the network's AI capabilities, supporting complex AI applications and facilitating industry-wide collaboration without compromising data privacy. In later sections, we will explore why CESS requires different types of miners and how each plays a unique role in ensuring decentralization, scalability, performance, and flexibility.
Let's take a deeper dive into the blockchain layer of CESS and understand its main technology stacks. The blockchain layer is the backbone of CESS, integrating several essential components: physical stack, network stack, data stack, consensus stack, and incentive stack. Each of these components plays a crucial role in ensuring the efficient and secure operation of the CESS network. Starting from the bottom, we have the physical stack. The physical stack offers three important types of global resources: computing, network, and storage. Computing resources handle performance and task scheduling, primarily managed by the consensus node and the Trusted Execution Environment, or TEE node. Network resources ensure efficient and high-speed communication, managed by the content delivery nodes, and storage nodes provide reliable data storage offered by the storage nodes. Next, we have the network stack. The network stack leverages DHT technology within a peer-to-peer network, enabling seamless communication and data transfer between nodes. This decentralized approach allows for efficient sharing of information and responsibilities, making the network robust and scalable. The network stack primarily consists of peer-to-peer protocol, gRPC, fault tolerance, root discovery, and many more. On top of the network stack, we have the data stack. The data stack is crucial for storing blockchain data like transaction mechanisms, data fingerprints, and other file-related metadata. It employs various tools like digital signatures and hashing algorithms to ensure the security and integrity of user data throughout its lifecycle. Next, we have the consensus stack. The consensus stack utilizes random rotational selection, or R²S, method for block authoring. This is combined with the Grandpa consensus algorithm, which selects random validators using VRF technology to ensure quick consensus among nodes. Additionally, it employs different storage-related proof algorithms to verify that the storage nodes are fulfilling their promise of providing and storing user data. Lastly, we have the incentive stack. The incentive stack manages file storage and cache nodes, distributing reward based on the resources contributed by nodes. This incentivizes participation and ensures the network's growth and stability. Now let's talk about the distributed storage resource layer. The distributed storage resource layer is composed of two types of nodes: storage nodes and consensus nodes. These nodes communicate using a peer-to-peer protocol. Storage nodes are responsible for providing storage space to the network and storing user data, while consensus nodes validate transactions, generate blocks, and create challenges for the storage nodes to ensure file integrity and authenticity. Incoming file segments from the content delivery layer nodes are encrypted, replicated, and shared before being stored by the storage nodes. The file is initially triplicated by default, giving options for the users to have more copies, but of course that will come with a price. Each of the 3 copies of the files is then sharded and erasure encoded to ensure data availability. The file segments are distributed to multiple storage nodes to enhance the security and redundancy of users' files. Additional computations are performed on the file segments to generate file tags, which are used for CESS proof of data reduplication and recovery, as well for the proof of ideal space mechanism, which ensures storage nodes fulfill their commitment by providing storage space and storing users' data. Furthermore, this layer also integrates AES encryption for storing private data and provides role-based access with multi-factor authentication to the stored data. Next, let's explore the Content Delivery Distributed Network, or CD²N layer. We will begin by examining how retrieval nodes and cache nodes work together, followed by a discussion of the key functionalities and features this layer provides. First, let's delve into the working process of the CD²N layer. When a user uploads a file, it is initially handled by the retrieval node. In this current version of CESS testnet, both the retrieval node and cache node are implemented within the DOS, which was covered in detail in later sections of this course and of course mentioned in the first episode. In future versions, these will be separated into distinct nodes. When a user uploads a file, the retrieval node validates the user's storage space on the CESS network. Users must have pre-purchased storage space to upload any files. Once validated, the file is sliced into smaller segments, erasure encoded, and then distributed to various storage nodes. During this process, metadata such as the file name, segment ID, and chunk location are recorded on the blockchain. This metadata plays a crucial role when retrieving files. The retrieval node uses it to locate and reassemble the file segments from the storage nodes, ensuring the file is accurately reconstructed and delivered back to the user. On the caching side, frequently accessed files are stored in the cache node closest to the user. This proximity ensures that subsequent requests for the same file can be fulfilled with minimal latency, significantly enhancing the user experience. Additionally, based on the policy set by the file owners, users may be required to pay to retrieve the file. The CD²N layer provides various cutting-edge functionalities and features to the CESS network, such as the dynamic load balancing feature ensures efficient traffic distribution across multiple nodes. This is achieved through sophisticated algorithms that prevent any single node from becoming a bottleneck, thereby optimizing the network performance and reducing latency. Edge computing is another vital feature. By processing data closer to the end users, the CDN² layer reduces latency even further. Edge nodes can perform real-time data processing and caching, which significantly enhances the user experience. Scalability and elasticity are also integral to the CDN² layer. The system is designed to scale elastically based on demand. During peak times, additional nodes can be added to handle the increased nodes, while during off-peak time, resources can be scaled down to save costs during these decreased loads. Security and privacy, of course, are paramount. The CD² layer incorporates advanced security protocols to ensure data integrity and privacy. Encryption techniques and secure key management protect data during transmission and storage, while blockchain technology provides a tamper-proof record of all transactions. Fault tolerance is another critical feature. The network is built with mechanisms to detect and mitigate node failures. If a node goes offline, the system automatically redirects traffic to other available nodes, ensuring uninterrupted service. The CDN² layer also includes comprehensive analytics and monitoring tools, providing real-time insights into network performance, user behavior, and content popularity. This data helps optimize content distribution and improve overall efficiency. Interoperability with other networks is a significant advantage for CESS. The CD²N layer is designed to seamlessly integrate with other CDN and peer-to-peer networks, expanding its reach and capabilities. Finally, energy efficient is a key consideration. The CD²N layer includes an energy-efficient protocol and hardware configurations to minimize the carbon footprint of the network. By optimizing resource utilization and employing green technologies, the system promotes sustainability. In summary, the CDN² layer within the CESS ecosystem leverages the combined efforts of retrieval nodes and cache nodes to optimize data access and delivery. With advanced features like dynamic load balancing, edge computing, and fault tolerance, this layer ensures a robust, efficient, and scalable content distribution network, providing users with fast, reliable, and secure data access in a decentralized network. Now let's overview the CESS AI link. CESS AI link is a pivotal component of the CESS AI protocol suite. This advanced technology is designed to revolutionize secure and efficient machine learning in decentralized environments by enabling collaborative AI training without compromising data integrity. At the heart of the CESS AI link is its focus on privacy and data sovereignty. Users or organizations can collaboratively train AI models in a decentralized network, ensuring their raw data remains private. During the model training period, the CESS AI link leverages smart contracts to delegate local model training tasks to various computing nodes within the CESS network. These computing nodes can range from CPUs and GPU clusters to decentralized GPU computation. The system integrates federated learning mechanisms, allowing participants to train shared models without sharing their original data. Computational tasks are delegated to various nodes, ensuring efficient use of resources while maintaining data sovereignty. This approach enables participants to engage in AI training at any time, revolutionizing secure and efficient machine learning processes in decentralized environments. Different organizations often have private data that cannot be shared due to sensitivity or legal issues. The CESS AI link allows these organizations to collaboratively train AI models without exposing their original sensitive data. For example, in the medical field in most countries, medical data is extremely sensitive and important to individuals. Patients are often concerned about sharing their medical data due to privacy issues. However, with the CESS AI link, patients can rest assured that their data will not be leaked. This technology allows their data to remain private while still contributing to the training of AI models. Hospitals and medical institutions can use this federated learning approach to develop better diagnostic tools and treatment plans without compromising patient privacy. This way, the medical community can achieve AI-driven healthcare solutions while ensuring that the individual's medical data remains secure. Integrating this CESS AI link provides a robust and efficient and scalable solution for collaborative AI training. This multifaceted approach ensures high-quality, privacy-preserving AI model development and enabling technologies and organizations to create versatile AI models that address complex challenges across industries. In the coming sections of this episode, we will address the challenges of the decentralized industry. To provide clarity, we have segmented these challenges And for each challenge, we will discuss the specific key technology implemented in the CESS network to address them. We will cover 6 challenges and 6 key technologies one by one. The first challenge is data vulnerability, which is faced by the decentralized storage industry. This is a major concern for the storage industry as it presents significant challenges. Our data is constantly at risk due to unexpected node failures, which can result in permanent data loss, impacting data availability and integrity. To address this challenge, we need a robust redundancy and recovery mechanism that can withstand node failures. In a decentralized network where open participation is the primary focus, users have the freedom to leave the network at any time. This is a concern for storage nodes. If the nodes storing our data decide to leave the network, it can lead to loss of our data and storage capacity. To encourage storage nodes to actively participate in the network, it's crucial to incentivize long-term participation. That being said, allowing open participation introduces an extra layer of vulnerability because of inadequate system configurations and users' lack of security knowledge. This can enable hackers to access the system and compromise users' data or delete it entirely. As a result, the system should incorporate advanced encryption and security protocols to counter these threats. To address all of those issues, CESS provides a solution to this problem by utilizing its proof of data reduplication and recovery technology, PODR², and proof of ideal space, or POIS, algorithms. Challenge number 1 solution is the PODR². So to address the challenge of ensuring that files are stored safely and correctly on the hard disk, CESS provides a robust proof of data reduplication and recovery solution. PODR² is a sophisticated storage proof mechanism designed to guarantee the integrity and availability of data within the CESS network. This solution offers several critical features. Publicly verifiable managed continued proofs. PODR² ensures that data storage is continuously monitored and verified through publicly accessible proofs. This transparency allows for constant oversight and validation of stored data. Storage proof based on data copies. The mechanism relies on redundancy of data concepts and data copies to verify that files are stored correctly. This approach ensures that even if a node fails or data is lost, copies are available for recovery. Data integrity, rapid recovery mechanisms. In the event of data corruption or loss, PODR² provides a rapid recovery process ensuring that data integrity is maintained and any issues are swiftly addressed. Ultra-compressed aggregated proof and batch verification. PODR² utilizes highly efficient compressed proofs for verifying data storage. This aggregation of proofs allows for batch verification, enhancing system efficiency and reducing overhead. Rapid verification and error localization. The system quickly enables verification of data integrity and precise location of errors, facilitating prompt resolution and minimizing potential disruptions. Key revocation and updating. To further secure data, PODR² incorporates mechanisms for key revocation and updating. This ensures that access controls remain effective, up-to-date, and protect against unauthorized access. The Challenge 1 PODR² workflow is designed to ensure data integrity and availability through a series of well-defined steps as illustrated in the diagram. The process begins with key generation within the trusted execution environment. This key is securely shared with other trusted execution environments that join the network, ensuring that the key remains protected from external access. Following this, the order place step involves the user or data owner placing an order for storage. Once the order is placed, the file is first replicated to create multiple copies for redundancy. This is followed by segmentation, where the file is divided into smaller segments. These segments are then encoded to enhance security and efficiency. After encoding, the sign generation phase produces cryptographic tags or signatures for each file segment. These tags, known as semi-authenticators, are crucial for subsequent proof calculations. The storage providers then store these authenticators alongside the file segments. In the tag gen stage, these semi-authenticators are utilized during PODR² verification cycle. The CESS network periodically generates challenges to the storage nodes. The nodes must compute and submit proofs to demonstrate that they are indeed storing the file segments as required. The network then performs verification to ensure the proofs are accurate and reliable. By continuously cycling through these steps, PODR² maintains robust data integrity and facilitates rapid error localization and recovery. If the storage node fails to provide proofs multiple times, the network will consider it either as the storage node having left the network or facing some issues, and will copy the missing segments from the storage node to a new storage node. To address the challenge of ensuring that idle storage space is properly managed and accurately reported, CESS employs the proof of idle space mechanism. While PODR squared is focused on verifying the integrity of user data, POIS specifically deals with the verification of idle storage spaces. So how does POIS ensure that idle storage space are correctly allocated and maintained? POIS tackles this by utilizing specific random generated data to fill these idle data storage spaces. This approach enables the accurate determination of the true idle space available on each storage node. Essentially, POIS provides a way to verify that storage nodes are not falsely reporting unused space and are instead correctly managing their idle capacity. The algorithm for generating idle files under the POIS involves several steps. Generate layer 0 for file 1, followed by generating layer 0 for subsequent files, such as file 2, file 3, and so forth. Each layer represents a level of data granularity and integrity. Then we calculate layer n nodes label, where the root of the Merkle hash tree, MHTR, from layer n1 is used as an input. This hierarchical structure ensures that each layer is validated based on the integrity of the previous layer, hence the n-1. Each idle file in layer n is based on the aggregated result of the Merkle hash tree roots from all the previous layers, ensuring that the integrity of the idle space is continuously verified through this multi-layered approach. By following this process, POIS ensures that idle space are accurately reported but also managed correctly, preventing misuse and maintaining the overall efficiency of the CESS storage network. Challenge number 2 is data ownership. Ownership rights pose a significant challenge in the digital world. The issue at hand includes a lack of data origin verification, rampant cyber piracy, and the negative impact these problems have on content creators. There is no market solution that effectively addresses these issues, leading to various problems that significantly impact content creators and intellectual property rights. One major issue is a lack of data origin verification. Without the ability to accurately determine the original creator of the data, it becomes extremely difficult to establish authenticity and provenance. This gap in the verification process undermines trust and complicates the protection of intellectual property rights. Another significant challenge is, of course, cyber piracy. Unauthorized copying and distribution of digital content poses a severe threat to intellectual property rights. Cyber pirates can easily replicate and distribute content without permission, depriving the original creators of their due credit and financial benefits. This rampant piracy undermines the value of genuine content and rewards the wrong parties. The consequences of these issues are profound for content creators. When their work is pirated, they suffer a loss of revenue and recognition. The erosion of trust in the system discourages creators from producing original content, as they see their efforts being unfairly exploited. This negative impact not only affects individual creators, but also stifles innovation and creativity in the broader digital landscape. To address these challenges, CESS has developed a multi-format data rights confirmation mechanism, or MDRC. MDRC offers a robust solution to ensure data origin verification, protect against cyber piracy, and support content creators. Let's have a look at MDRC, or Multiple Format Data Rights Confirmation Mechanism, in detail. MDRC is essential for ensuring data rights protection within the CESS network. The way it works is by assigning a unique data certificate ID to each file by extracting a data fingerprint. This fingerprint is generated using advanced algorithms tailored for different file types. For text files, for example, MDRC uses advanced word segmentation techniques. For photos, it analyzes colors, textures, shapes, and spatial information, among other characteristics. Once the fingerprints are extracted, the MDRC mechanism performs fingerprint comparisons using SIMHASH. SIMHASH is a technique used to detect similarities between datasets efficiently. By comparing these fingerprints, the system can confirm the uniqueness and integrity of the data. The next step involves generating a unique certificate ID for each file, which is then stored on the CESS blockchain. This certificate acts as a proof of data rights confirmation, ensuring that the data ownership and integrity are verifiable and secure. The diagram accompanying this explanation shows users at the bottom interacting with the decentralized data storage, or the CESS network. When users upload files, the MDRC extracts fingerprints based on the file type. The SIMHASH function checks for similarities, ensuring data integrity and rights protection. This process ensures that data stored within the CESS network is not only secure, but also has verifiable proof of ownership and integrity, making it an ideal solution for protecting valuable digital assets. By integrating these advanced features, the MDRC mechanism upholds the high standards of data security and rights protections that are critical in today's digital landscape. Challenge number 3 is an inefficient network. Another significant industry challenge is the inefficiency of blockchain networks. While blockchain technology is known for its decentralized and transparent nature, paving the way for innovative solutions across various sectors, it grapples with network inefficiencies. These inefficiencies not only affect the performance of blockchain networks, but also influence user adoption, node participation, and the overall health of the ecosystem. As we navigate the landscape of blockchain network efficiency, 3 key issues come to the forefront. First, low transactions per second, or TPS. Many blockchain networks face limitations in processing speeds, which hinders their ability to scale and handle a high volume of transactions seamlessly. This challenge significantly impacts the efficiency and responsiveness of blockchain applications, posing a barrier to widespread adoption. When a network can't handle a large number of transactions efficiently, it slows down the entire system, leading to delays and decreased user satisfaction. Second is high transaction fees. During periods of network transactions, transaction fees can skyrocket, presenting a significant obstacle for users. These elevated costs diminish the cost-effectiveness and accessibility of blockchain transactions, deterring users from engaging in everyday activities on the blockchain. For developers and businesses looking to integrate blockchain technology, these high fees can also be a barrier to entry, limiting the potential for broader application and innovation. Third, the lack of average nodes incentives. For a blockchain network to remain secure and decentralized, it is crucial to sustain consistent and attractive rewards for nodes. However, many networks struggle with providing sufficient incentives, leading to low participation. When nodes are not accurately rewarded, it becomes difficult to maintain a robust and secure network, as fewer participants may be willing to contribute their resources and efforts. To address these inefficiencies, CESS has developed a key technology called Random Rotational Selection Mechanism. The Random Rotational Selection, or R2S consensus protocol, is central to enhancing both scalability and efficiency within the CESS network. By streamlining transaction processing, R2S ensures that transactions are handled swiftly and securely, optimizing overall network performance. At the core of random rotational selection is the principle of providing equal opportunities for all nodes. Every node in the CESS network has the potential to become a consensus node thanks to a staking mechanism that places no limits on participation. This inclusivity is further supported by a credit rating system that assesses the nodes based on their performance. Nodes that meet the required performance standards are elevated to candidate consensus nodes. From this pool of candidate nodes, the protocol employs a verifiable random function, VRF, to randomly select 11 on-duty consensus nodes. This random selection process ensures fairness and prevents bias as the nodes are chosen without prejudice. These 11 nodes then take turns validating transactions and producing blocks in a round-robin sequence. Furthermore, the 11 nodes are elected again in each year, which is 6 hours in the CESS testnet. Additionally, consensus nodes have the option to use the trusted execution environment. Utilizing a trusted execution environment can provide a node's credit rating, thereby increasing its chances of being selected as the candidate consensus node. The TEE also plays a crucial role in the proof of data reduplication and recovery, helping to verify that storage nodes are indeed fulfilling their storage requirements each year. In summary, the R2S consensus mechanism effectively addresses several economic and performance challenges faced by blockchain networks. By distributing the consensus workload evenly, reducing transaction costs, and incentivizing nodes through a fair and transparent selection process, random rotational selection contributes to a more scalable, efficient, and sustainable blockchain ecosystem. Challenge number 4 is no private data sharing. A significant challenge facing the decentralized storage industry today is the secure handling of private data. Many existing solutions struggle to adequately manage sensitive information, leaving users with limited control over who accesses their data. One major issue is the lack of supportive private data. Current infrastructures often fail to provide robust mechanisms for handling sensitive information securely. This gap in infrastructure means that users are unable to effectively control who has access to their data, leading to concerns over privacy and security. Additionally, the absence of effective encryption mechanisms exacerbates the problem. Data that is transmitted and stored without encryption is highly vulnerable to unauthorized access. This lack of encryption increases the risk of data breaches, exposing private information to potential threats. Moreover, the industry has seen frequent incidents of data leaks, undermining user trust and raising potential legal concerns. These breaches not only compromise individual privacy, but also damage the credibility of decentralized storage solutions, highlighting the urgent need for more secure and trustworthy systems such as CESS. To address the challenge of securely storing and sharing private data, CESS introduces a cutting-edge solution known as proxy re-encryption. Proxy re-encryption technology enables users to share files without the need to decrypt them. Let's break down exactly how this works. To illustrate how this works, we'll walk through an example involving Alice and Bob. Imagine Alice wants to send a confidential message to Bob, but only wants Bob to be able to access it while keeping the message encrypted in transit. Here's how proxy re-encryption technology facilitates this process. Alice starts by encrypting her message, denoted as M, using her own public key, PKA. This results in ciphertext CA, which represents the encrypted version of the method. To delegate access to Bob, Alice needs to create a re-encryption key. This key is generated using her secret key, SKA, and Bob's public key, PKB. The re-encryption key, RKA to B, is created through a function called rekey, which takes SKA and PKB as input. For re-encryption, the ciphertext CA is then sent to the DOS proxy, which is use the re-encryption key RKA to B to transform CA into a new ciphertext, CB. This re-encryption process effectively allows the proxy convert to the encrypted method into a format that can be decrypted by Bob so he can read the message. Once the ciphertext CB is created, Bob can use his own secret key, SKB, to decrypt CB. This decryption process reveals the original plain text message M, which was encrypted by Alice, but now accessed securely by Bob. This mechanism ensures that while Alice's message remains encrypted, it can be securely shared with Bob without needing to decrypt it first. Proxy re-encryption provides a robust solution for securely managing and sharing encrypted data, safeguarding it against unauthorized access, while enabling authorized parties to present access to the content. Challenge number 5 is maintaining and training AI models without exposing original data. Now, to address challenge 5, as we all know, AI algorithms require large datasets to train an AI model effectively. These datasets often contain sensitive information, raising privacy concerns, and without robust privacy mechanisms or measures, there is a substantial risk of data misuse and breaches of users' privacy. For instance, we saw in an example earlier in the healthcare sector, hospitals possess vast amounts of patient data that can significantly increase the AI's diagnostic tools. However, sharing this sensitive medical data openly for training purposes could lead to severe privacy violations and misuse of user data. Additionally, most people are unwilling to share their medical records. Can you imagine if training data without sharing content itself could be possible? The solution to these challenges lies exactly in training data without sharing the content itself. This approach allows the use of vulnerable data for AI model training without exposing the actual data, thereby preserving the user's privacy and ensuring compliance with ethical standards. For example, hospitals would be able to collaborate and create powerful AI models for diagnosing disease without sharing the sensitive data. The CESS AI link is the solution to this challenge. The CESS AI link is a Byzantine robust circuit designed with a strong focus on data privacy. It allows for the training of AI models in a decentralized network without exposing the original data. This approach ensures that sensitive information remains secure while still enabling effective AI training. Key advantages are decentralized computing, where the CESS AI link leverages decentralized computing to allow multiple nodes across the network to participate in the training process. This decentralized approach enhances the robustness and security of the AI model training. Coordinate training rounds division by smart contracts. Smart contracts play a crucial role in coordinating the training process. They divide the training rounds and manage the distribution of tasks among different nodes, ensuring an efficient and orderly training workflow. Easy integration with other GPU networks, which is how the CESS AI link is designed to be easily integrated into other GPU networks. This compatibility allows for seamless collaboration and utilization of GPU resources across various platforms, enhancing the overall computational power available for AI training. Can be accelerated by hardware. The system can be accelerated by hardware, providing additional computational speed and efficiency. This hardware acceleration ensures that the AI model training process is both fast and effective, meeting the demands of complex AI tasks. As you can see in the diagram, multiple organizations, org 1, 2, 3, and 4, are able to communicate via the Decentralized Object Storage System, or DOS. The CESS AI link is embedded with a smart contract that runs on the CESS blockchain. The setup allows organizations to train AI models collaboratively without sharing the original data. The smart contract ensures the coordination and privacy of the training process across the decentralized network. The last industry challenge that we will discuss in this course is the inefficient use of storage space. Currently, many decentralized storage systems lack cloud pooling functionality, which means that storage nodes often operate in isolation. This leads to the underutilization of available resources and the wastage of storage space. Without mechanisms to aggregate and efficiently utilize storage resources, unused storage remains idle, contributing to increased costs and inefficiencies. This issue is particularly evident in systems like Filecoin, where storage capacity is not always optimally utilized, leading to potential wastage and higher operational costs. To tackle these inefficiencies, CESS has introduced a smart space management system. The smart space management system is designed to manage the entire network's storage space effectively. The system accommodates nodes that have varying amounts of storage and computing resources, ensuring efficient utilization across the network. It employs a robust space management mechanism that prevents malicious activities, ensuring that storage space is used effectively and securely. The Smart Space Management System classifies storage space into three categories: unverified space, idle space, and active space. Unverified space is initially reported by the storage node and specified in the node's configuration. Nodes must stake 4,000 CESS tokens per terabyte of unverified space, but this space does not earn rewards until it is verified. Idle space is verified by the CESS network and is available for purchase by the users. Nodes can store users' data in this space and even earn rewards for doing so. Active space is a verified space that actively stores user data. Nodes earn higher rewards for storing data in active space. In the diagram, we see a total of 1 terabyte of storage space allocated by the storage miner, initially classified as unverified space. Over time, this unverified space is verified by the CESS network and filled with a spaceholder file generated by the trusted execution environment. This file is also verifiable through the proof of idle space mechanism. Before user data can be stored, the storage space must be verified. Once verified, the space becomes idle space. When a user uploads a file, the idle space is replaced with user data, transforming it into active space. As depicted in the diagram, the storage node initially holds 1 terabyte of unverified space. Over time, this is verified, and as user data is uploaded, the node transitions to holding 0.4 terabytes of active space and then 0.1 terabytes of idle space. In summary, the Smart Space Management System optimizes the use of storage space within the CESS network. By classifying storage into unverified, idle, and active spaces, it ensures efficient and secure storage, maximizing rewards for storage nodes and enhancing overall network performance. Now let's walk through the stages of the Smart Space Management System. Stage 1 is filling idle space. The process begins with the storage node reporting its allocated storage space to the blockchain. This is the starting point where the network recognizes the available space that can be managed. Next, the storage node requires idle data from the trusted execution environment. This TEE is typically managed by consensus nodes but can also operate independently, and it generates verifiable random data. The metadata of this data is recorded on the CESS blockchain, ensuring that the data's integrity and origin are verifiable. The trusted execution environment then sends a spaceholder file back to the storage node. This file signifies the previously unverified space has now become verified space. Stage 2 is storing users' data. When a user uploads a file, the storage node replaces the previously generated idle data with new user data. This transition from idle data to user data is reported back to the CESS blockchain, and the storage node updates its storage information accordingly. This ensures that the space previously occupied by idle data is now actively used for storing user content. Step 3 is the challenge and reward. In the final stage, the CESS blockchain periodically issues challenges to storage nodes. These challenges require the nodes to submit proofs that they are indeed storing the user's data as expected. If the storage node successfully completes the proof and verifies that data is intact, it is rewarded with CESS tokens. This incentivizes the storage nodes to maintain high standards of data integrity and reliability. The diagram visually represents these stages, starting from the reporting of allocated storage space to the blockchain, requesting and generating verifiable random data, replacing idle data with user content, and finally the periodic challenges and reward system. This structured approach ensures efficient management and verification of storage space within the CESS network. In this slide, we delve into the storage node space management, focusing on how storage nodes handle and manage their allocated space within the CESS network. Let's break down the key aspects and how they are depicted in this diagram. First are regular checks. Storage nodes are responsible for maintaining and updating their space utilization efficiently. When a user's data is stored, any previously allocated idle space that is no longer needed is deleted. This action is promptly reported to the CESS blockchain, ensuring that the network is kept up to date with accurate space usage data. Consequently, the amount of active space increases while idle space decreases. Cleanup To ensure the integrity and efficiency of the storage network, regular cleanup operations are necessary. This involves removing any invalid or outdated data to maintain a valid data storage environment. The command for manual cleanup is known as bucket tidy, which can be executed to perform these maintenance tasks as needed. The diagram overview. This diagram illustrates the storage node space management. Idle space. This section of the diagram shows various segments of idle space represented by I-1, I-2, and I-3, etc. This space is initially unverified and is filled with hashes as placeholder data until user data replaces it. Active space. This area contains user data hashes such as S-1, S-2, etc. This space is actively used for storing data and is crucial for meeting user storage requirements. The remaining disk space represents the available space on the storage nodes after accounting for both idle and active space, which is the unverified space. On top of the storage nodes is the CESS chain, which manages and communicates with each storage node. The CESS chain maintains a comprehensive record of the entire network storage capacity, including unverified space, which is the portion of the network's total storage that has not yet been verified, idle space, space that is verified but not currently in use, and active space, space actively storing user data. The diagram also shows storage node's specific contribution to this network-wide data management, displaying its idle space and active space in relation to the overall network storage power. Now let's take a look at the client interaction model. We will start from the top of the diagram and work our way down. On the left, we have the client followed by the CESS gateway, and then the blockchain and storage nodes. Most of the time, the client interacts with the gateway only via API call. The gateway in turn sends requests to the CESS blockchain or storage nodes. The blockchain layer represented in the third column is run by consensus miners, while the storage node layer is managed by storage node miners. Users with technical knowledge can also directly query the CESS blockchain, which is built on Substrate. Therefore, all API endpoints and RPC call protocols for Substrate are applicable to the CESS blockchain. First, the user inquires about the price of storage. The blockchain layer returns the price, and then the user proceeds to pay or rent the specific storage space. They then define how much space they need for how long and make the payment. Next, the user uploads their data via the gateway. The data is sliced into multiple pieces and encrypted. Each piece has proof computed, and these pieces are distributed to different storage nodes, completing the upload process. Meanwhile, behind the scenes, the blockchain and storage nodes continuously interact. The blockchain sends two kinds of challenges to storage nodes: the space provision challenge, ensuring that storage nodes are indeed providing the claimed space, and the data integrity challenge, ensuring that storage nodes are storing user data properly without tampering or deletion. Storage nodes must compute proofs to respond to these challenges, otherwise they risk having their stake slashed. Now for the download process. If the data is gated for payment, the user must first make a payment. Then the user initiates the download. The gateway retrieves all the different slices, reassembles them, and finally the data is returned to the user. This is the client interaction model, demonstrating how users interact with the CESS network for uploading and downloading data securely and efficiently. So we've covered a lot of theory. Next, we will dive into user roles and their participation in the CESS network. We'll also focus on building decentralized applications, dApps, on CESS using Inc. smart contracts. This latter part will be more developer-centric, so get ready to roll up your sleeves and start coding. Thank you for your attention, and I look forward to seeing you in the next episodes. Have a great day.